Welcome back, everyone, for another deep dive.
Mm-hmm.
This time we're looking into Curium.
Curium.
And I know what you're thinking.
Oh, yeah.
Named after Marie and Pierre Curie, right?
Of course it is.
Yeah, but
It is.
did you know it glows in the dark?
Oh, wow.
It's true.
That's pretty neat.
It is. We're going to unpack how that's even possible by digging into some excerpts from Curium's Wikipedia page.
Wait.
And I have an expert here.
Yeah, this is really fascinating because unlike most elements, you don't just find curium out in the world.
Make sense of it all.
Every single atom of it was created.
Right.
By us in a lab.
Yeah, we made this element, so where do we even begin with a story like that?
Well, the story starts back in the 1940s at the University of California, Berkeley. Okay, so picture this. World War II is raging. The Manhattan Project is in full swing.
Oh, wow.
And there's this intense pressure to make scientific breakthroughs.
Huge pressure.
And that's where our main characters come in. Glenn T. Seaborg, Ralph A. James, and Albrecht Urso.
These are the guys.
Yeah.
Okay.
And they were working on creating new elements. And in 1944, they managed to create Curium-242 by bombarding plutonium-239 with alpha particles
Incredible.
in a cyclotron.
Yeah, I can't even imagine what that must have been like.
And you know, they faced a big challenge in actually separating curium from another element.
Oh, really?
That they created around the same time, americium.
Oh.
It was so difficult that they nicknamed these elements pandemonium and delirium.
Uh-huh. Scientists with a sense of humor.
I know.
But I guess when you're dealing with brand new elements, a little chaos is expected.
Absolutely. But they eventually identified Curium-242 through its unique alpha decay signature.
Okay.
But here's the really interesting part.
Okay.
Before the official announcement, Seaborg actually leaked the discovery on a children's radio show called Quiz Kids.
Wait, seriously? Yeah. He's just casually dropped this groundbreaking
I know, right?
Scientific discovery on a kid's show. That's amazing.
I know, right?
So, okay, they discover this new element.
Yeah.
What does it even look like?
So it's a hard, dense, silvery white metal.
Okay.
But it's far from ordinary.
Okay.
Curium has some unusual properties, especially when you compare it to other actinides.
Okay.
For example, its melting point is 1,344 degrees Celsius.
Wow, that's hot.
It's incredibly hot.
Most metals would be a puddle at that temperature.
Exactly. It's quite surprising.
Yeah.
And then there are its magnetic properties.
Okay.
As curium cools, it transitions from a paramagnetic state to an antiferromagnetic state. And what's even more interesting is that it shares this characteristic with its lanthanide counterpart, gadolinium.
So these two elements from different parts of the periodic table, they behave similarly.
Yes.
That seems like an important clue about their underlying structure.
You're right. The periodic table isn't just this random arrangement. There are these hidden connections and patterns that reveal a deeper order. Totally.
Yeah.
And these patterns extend to curium's chemical behavior as well.
What do you mean?
Well, curium tends to exist in a +3 oxidation state.
Okay.
Just like many lanthanides.
Okay.
This gives curium ions a pale green color when dissolved in solution.
Okay.
It can also exhibit a +4 state, but it's less common and usually found in solid forms.
Like curium dioxide, which I think is pale yellow in solution.
Yes, pale yellow.
So pale green, pale yellow, not the most vibrant colors in the world. But wait, there's also a +6 state, right? The curl ion?
Yes, but that one is incredibly elusive. It's only been reported once.
Really? Wow. Okay, so we've got this element that glows in the dark, has high melting points, and some interesting magnetic properties.
Yeah.
Now let's dive into what really sets curium apart. Its radioactivity.
That's a key aspect of curium. All known isotopes of curium are radioactive.
Oh, wow.
But what makes this really interesting for us is that some of these isotopes have incredibly long half-lives, which means they decay very slowly.
Like Curium-247, which has a half-life of 15.6 million years.
Exactly. And Curium-248 with a half-life of 348,000 years.
That's longer than humans have been around.
I know. It's incredible.
Yeah, why are these long half-lives so important?
Well, they make these isotopes ideal for research.
Okay.
They're relatively stable, allowing scientists to study their properties in depth.
Right.
However, even with these longer-lived isotopes, obtaining specific ones can be incredibly challenging.
Because they exist within these intricate decay chains.
Yeah, like trying to pluck a single thread from a giant tangled mess.
Right, yeah.
A very apt analogy.
Yeah.
And then there's Curium-250,
Okay.
which primarily decays through spontaneous fission.
Spontaneous fission. That sounds intense.
It is. Instead of just emitting particles, the atom actually splits apart.
Wow.
And this brings us back to that glowing metal fact we mentioned earlier.
Right. That's what I'm most curious about.
Yeah.
It's like something out of a sci-fi movie.
Well, it's due to curium's intense radioactivity, and this causes it to emit a purple glow in the dark. It's almost poetic, considering it's named after Marie Curie, who pioneered work with radium, another luminescent radioactive element.
That's incredible.
Yeah.
But aside from this cool visual effect, how do we actually use curium?
Well, Curium-244 was initially considered for use in radioisotope thermoelectric generators,
Okay.
but its high cost and neutron emission made it impractical.
Too bad. But I read that curium has some other surprising uses, especially in space exploration.
That's right.
Really?
Curium has become essential for understanding the composition of other planets and celestial bodies. It's used as an alpha particle source in those amazing APXS instruments.
APXS.
Yeah, alpha particle X-ray spectrometers, which are like portable curium-powered labs.
Wait, so these instruments are using curium's radiation to analyze stuff on other planets?
Exactly.
It's incredible that we can use something we made here on Earth to study the cosmos.
It really highlights the ingenuity of scientists and their ability to harness even the most seemingly dangerous forces for good.
Absolutely. Okay, so how do these APXS instruments actually work?
So the curium inside the instrument emits alpha particles. Think of them as tiny, high-energy projectiles.
Okay.
And these particles bombard the target material, say a rock on Mars.
Okay.
And by analyzing how the alpha particles scatter or what kind of X-rays they excite in the process, we can figure out the elemental composition of that rock. It's like a high-tech game of atomic billiards.
That is so cool. It makes you wonder what other secrets of the universe are hidden within the elements we're still discovering.
There's always more to uncover.
For sure.
Speaking of secrets, we've talked about curium's high melting point.
Yeah.
But have you ever wondered about its density?
Not really.
Okay.
But now that you mention it, I'm curious.
Okay, so curium's density is 13.52 grams per cubic centimeter.
Okay.
That's denser than most metals.
Okay.
But interestingly, lighter than its neighbors on the periodic table, neptunium and plutonium.
Wait, so it's denser than most metals, but lighter than its neighbors. That seems like a contradiction.
It's a bit of an anomaly.
Yeah.
And scientists are still exploring why that is. It could be related to the way curium's atoms are arranged in its crystal structure. And speaking of structure, did you know curium can actually exist in two different crystalline forms?
Two different forms. What are they like?
So there's alpha curium, which is the most stable form at room temperature.
Okay.
It has a hexagonal symmetry.
Good.
But under high pressure, it can transition to beta curium, which has a face-centered cubic structure.
So if we squeeze curium hard enough, it actually changes its structure. That's pretty wild. Does this change in structure affect any of its other properties?
It can. For example, the transition from alpha curium to beta curium affects its magnetic behavior.
Oh, right. We were talking about that earlier.
Yeah.
The whole paramagnetic to antiferromagnetic shift that it shares with gadolinium.
And these changes in magnetic properties can also influence a material's electrical conductivity.
So squeezing curium could potentially change how well it conducts electricity. It's amazing how something as simple as pressure can have such profound effects.
It's a reminder that even the most basic physical forces can dramatically alter the properties of matter.
Right.
And these changes can be difficult to predict and fully understand.
Absolutely. You know, we talked about curium's radioactivity, making it difficult to handle.
Right.
But are there any other challenges in studying this element?
There are quite a few.
Like what?
For instance, accurately measuring curium's electrical resistivity is notoriously difficult.
Why is that? What makes it so tricky?
It all boils down to alpha decay.
Okay.
As curium undergoes alpha decay, those emitted particles cause damage to its own crystal lattice, and this damage over time increases its electrical resistivity.
So it's like its own radioactivity is constantly changing its electrical properties.
Exactly. It's like trying to hit a moving target.
Right. It makes you wonder, what other secrets are hidden within this element? What are scientists still trying to figure out about curium?
There are many unanswered questions. For example, we're still learning about the intricacies of curium's fluorescence.
Fluorescence? You mean it glows under UV light, too?
Exactly. When curium ions are exposed to ultraviolet light, they emit a beautiful yellow-orange fluorescence.
I never knew curium was so colorful. I thought it was all pale greens and yellows.
It can be quite striking.
Well, but what's the point of this fluorescence? Is it just a cool visual effect?
It's actually a valuable tool for researchers.
Okay.
By analyzing the fluorescence, scientists can study how curium ions interact with various molecules in both organic and inorganic compounds. It's like having a built-in beacon that reveals those interactions.
Wow, so curium's fluorescence is actually helping us understand more about chemistry in general. It's amazing how something so radioactive can be so useful in unexpected ways.
It's a testament to the interconnectedness of scientific knowledge. Now, let's shift gears a bit and revisit the applications of curium.
Okay.
We talked about how curium-244 wasn't ideal for radioisotope thermoelectric generators.
Like because of the cost and those pesky neutrons.
Yeah.
But it's found a good home in space exploration, hasn't it?
Absolutely. Curium is crucial to the operation of those APXS instruments we discussed earlier.
Right.
The ones used to determine the elemental composition of materials on other planets and celestial bodies.
And thanks to curium, we've gained a lot of knowledge about Mars.
Indeed, APXS instruments with curium as their alpha particle source have been deployed on several Mars rovers, including Sojourner, Spirit, Opportunity, and Curiosity. They even played a key role in the Philae lander's mission to study Comet 67 Churyumov-Gerasimenko.
It's just mind-blowing to think that an element created in the lab here on Earth is helping us unravel the mysteries of our solar system. It really speaks to the power of human curiosity and ingenuity.
It does indeed. The story of curium is a fantastic example of how scientific discovery and exploration go hand in hand.
You know, learning about curium has been quite a journey.
It has.
But there's still so much more to cover.
There is, and we'll dive back into the fascinating world of curium in just a moment.
All right, we're back and ready to wrap up.
Yes.
Our deep dive into curium. It's been a wild ride.
It has.
From glowing metal
to
space exploration. And before we went on that short detour, we were talking about how curium is helping us learn about other planets.
Right, those APXS instruments.
Yeah, basically portable labs powered by curium.
Yeah.
Roving around Mars and even comets. It's like Star Trek.
I know. It's remarkable how those instruments work, bombarding materials with alpha particles.
Yeah.
Which are essentially helium nuclei.
Oh, okay.
By studying how these particles scatter or the X-rays they produce when they hit a sample, we can figure out what that sample is made of.
So curium's radiation is literally helping us decode the composition of planets and comets.
Exactly.
It's amazing how we've turned something potentially dangerous into a tool for discovery.
It speaks to human ingenuity. Yeah, our ability to harness the power of nature, even at the atomic level.
Totally. Okay, here's something I've been wondering about.
Okay.
If curium is so useful for space exploration, why aren't we using it to power spacecraft?
Right.
It seems like that natural radioactivity would be a perfect energy source.
That's a very logical thought.
Yeah.
But remember, curium's radiation requires careful handling and shielding. And those challenges become even more complex when you're talking about launching something into space.
Right. We wouldn't want a radioactive spaceship, whizzing around. Plus, there are concerns about contamination on other planets.
Safety is paramount when it comes to space exploration.
For sure.
And beyond those safety concerns, there's also the issue of efficiency.
Okay.
While curium is radioactive, its energy release isn't as easily controlled or as efficient as other power sources that are already being used in spacecraft, like solar panels or plutonium-based systems.
Makes sense. So for now, curium will stick to its role as an analytical tool in space.
Yeah.
I'm still in awe of the fact that we can create elements like this in the first place. It's like alchemy.
It is a remarkable feat of modern science, and the story of curium doesn't end there. Scientists are discovering new things about curium all the time.
Like what?
Well, certain curium isotopes are being investigated as a potential nuclear fuel.
Whoa, really?
Yeah.
So we might one day see curium powering our homes.
It's definitely a possibility.
Or even cities. That's mind-blowing.
It's a possibility, and one that researchers are actively exploring.
Wow.
Of course, with any nuclear technology, safety and waste management are crucial.
For sure. We have to be responsible with this kind of power.
Absolutely.
But it's exciting to imagine the potential. So what else is on the horizon for curium research? What are scientists curious about right now?
One fascinating area is nuclear transmutation.
Oh, yeah. Turning one element into another.
Precisely. Scientists are working on ways to transmute curium into less radioactive and shorter-lived isotopes, which would make storing it much safer and more manageable in the long run. This is especially important when you think about all the curium that's generated as a byproduct of nuclear power plants.
That's a great point. So if we can figure out how to, transmute curium into something less harmful, it could really change how we approach nuclear energy.
It could indeed. And that brings us to a really important point about curium.
Okay.
It's a reminder that many scientific discoveries, especially those involving powerful forces like radioactivity, often present us with a duality.
What do you mean?
Well, on one hand, curium is intensely radioactive, requiring careful handling and a great deal of respect. But on the other hand, it's this invaluable tool that's helping us unlock secrets of distant worlds and potentially paving the way for new energy solutions.
Yeah.
It's a perfect example of how something can be both a risk and an opportunity, a source of both concern and hope.
That's a beautiful way to put it. It's like curium embodies the challenges and the potential of scientific progress.
Exactly. And ultimately, I think the story of curium is a story about human curiosity and our drive to understand the universe, even in the face of the unknown.
I couldn't agree more. We started this deep dive with glowing metal and ended up talking about the future of energy and the very nature of scientific exploration. And that's the beauty of learning, isn't it? You never know where it'll take you.
That's true. Every element has a story to tell, a journey to take us on.
And that's what makes science so endlessly fascinating.
It is.
So, to all our listeners out there, we hope you enjoyed this deep dive into the world of curium.
Yes.
Remember, keep asking questions, keep exploring, and never lose your sense of wonder. You never know what incredible discoveries await